Good morning, everybody, or good afternoon or evening, whenever you're watching this. Okay, so lectures are online this year, which is very odd, but I usually try to record my lectures in the theatre anyway for you to follow up on. So perhaps actually the quality of these could be a little bit better. So welcome to the Part 2 Particle and Nuclear Physics course. My name is Tina Potter. I am a experimentalist in the High Energy Physics group here at Cambridge. I work on the ATLAS experiment and I'm looking for signs of something new and exciting, perhaps supersymmetry, something that will give us an answer to this massive question that we have about the dark matter in our universe. So I'm a hands-on experimental physicist. So if you have any questions about CERN or ATLAS and the LHC, I'm happy to answer those as well. And I have the pleasure of teaching you this course, not face-to-face this year, which is slightly sad, but we'll try and have as many online discussion sessions as we can so that you get to ask your questions to me. And we'll try and do our best with the interaction that we possibly can online. Okay, so let's get down to the slides, this introduction that I've got for you today. Right, so today I'm going to give you a roughly 45-minute introduction to the course. It's going to include all of the important information that you need for the course as well as a kind of outline. I know a lot of you are still making a choice on these optional courses. Okay, we've done that. So what we're going to be doing in this course is covering both particle physics and nuclear physics. So with particle physics, we're dealing with elementary particles. Those cannot be divided down any further. They're not comprised or composed of any other particles. We're also going to be dealing with the fundamental forces in nature. The electroweak force, which is actually the electromagnetic and the weak forces unified at higher energies, and the strong force. And all of these forces and particles, their interactions, are all embodied in something that we call the standard model of particle physics. And it's an extremely successful set of theories that describes all of the data that we see today, with a few interesting exceptions that we will talk about in the course. And then we'll be dealing with nuclear physics after Easter. And so this is the study of more complex nuclei, so not these elementary particles, but those that make up the complex nuclei, like protons and neutrons, which themselves are not fundamental particles. And they're bound together with the strong nuclear force. It's similar to the fundamental strong force, but at much longer scales. So we'll be talking about that as well. And weak and electromagnetic forces are also important for nuclear physics as well. Now, instead of a fundamental theory here, this is actually very difficult to understand from first principles. So simply because it's a very complex problem involving many different particles and forces as well. So what we'll be doing here is following a semi-empirical approach to try and understand what we see there. We'll be having a look at some simple models of nuclear physics, but there are a lot out there which you're free to go on to. So historically, of course, you had nuclear physics first, and then as our understanding and we were able to probe into smaller and smaller distances and higher energies, we started to understand particle physics. So nuclear physics came first and led to particle physics. But I'm going to turn that on its head for this course because many of the things that we'll be studying are common to both topics. And we'll be doing particle physics in Lent term and nuclear physics in the Easter term. So we'll have that break in between. We will start off, of course, with some introductory lectures that will be common for both of these topics. Okay, so the practical information is that pretty much all of the information for the course is on my website, and including these videos, of course, as well. It holds the notes, all the appendices, and the problem sheets as well. So if you don't manage to find your handouts or they're not to hand, everything is on the website there, including these videos. We're following two books here. For high energy physics, we're following Perkins, and for nuclear physics, we're following Crane. They are both excellent books, and I recommend you to get them and read them. I provide the lecturing material, these slides, in 3 handouts. So these are complementary to the books that we're following. So you have your formal notes in the books, and we have the lecturing material as we go through it as well. There are some gaps in the lecturing material. I know there are some gaps. They are there by design. In the lectures, we are going to be going through examples to try and highlight some of the information that I'm showing you. So I say please attend. We're not going to have in-person lectures anymore, but uh, they will be posted alongside the lectures on the website, so that you can fill in the gaps and work through them with me. And then for problem sheets that you'll be going through in your supervisions, there are 4 problem sheets that will hopefully match very well your 4 supervisions. They cover specific chapters in the course as well. 1, 2, and 1 covers the common introductory lectures. 2 and 3 cover particle physics, and problem sheet 4 covers nuclear physics. And then finally, my availability. I am very open to discussions and questions on this topic. I'm always surprised every single year when somebody ends up asking me questions that I cannot answer immediately, and I love that about this job. But my availability to you, it's typically before and after lectures. We don't have that, but I will book in slots where we can have informal discussions throughout Lent and Easter term that will take place of these before and after lecture chats that we usually have. Also, feel free to send me an email. And then if we need any sort of more in-person chats, we can do that, and we can meet online as well, one-to-one, if you want to discuss everything. So please do get in touch if you have anything that you want to ask about this course. Right, what I'm going to do in the next few slides is just give a quick overview of what we're talking about here. Much of this is new for everybody, but you are very familiar with matter, of course. So you're familiar with atoms. We've got those electrons whizzing around the nucleus, bound by the electromagnetic force. And the atom itself is about 10 to the minus 10 meters. The electron is much, much, much smaller. Of course, that's actually a fundamental particle. That's 10 to the minus 19 meters. And then atoms have all of these chemical properties that you're very familiar with, and that depends on how many electrons they have orbiting the nucleus, which in turn is dependent on, if you want a neutral atom anyway, the atomic number, the number of protons in that nucleus. So let's zoom into the nucleus here. These are nuclei, protons and neutrons, held together by the strong nuclear force. And the distances we're talking about here are about 5 times 10 to the minus 15 meters, 5 femtometers. Very, very, very tiny. And the binding energy that you have there compared to the atom is much, much higher, about 10 million times higher. So very, very strongly bound. And let's dive in a little bit deeper. Protons and neutrons are not fundamental particles. They are made up of quarks that are bound together by gluons. And that's the carrier of the strong force. Now, these are much, much higher bound, they're bound together with much, much higher energy in turn than the nuclei and the atoms, about 1 GeV. So that's 10 to the 9 electron volts. We're talking about much, much smaller distances, about 1 femtometer there. And we know the masses of the protons and neutrons that the ups and down quarks and the gluons all make up as well. So these are the nuclei, what we're going to be talking about for nuclear physics, and then the quarks and the electrons and the other fundamental particles are what we're going to be discussing for particle physics. So let's have a look at these fundamental particles. In the Standard Model, we understand that matter is made up of fermions, these spin half fundamental particles. And there's 2 types. There's leptons and there are quarks. And you may be very familiar with some of the leptons, for example, the electron. And then it's got a heavier version, which is the muon, and an even heavier third version there, which is the tau. So these are the 3 generations, and they tend to increase in mass as you go up. And we also have, for each of these charged leptons, we have a neutral particle called a neutrino, which is pretty much massless. The other type that we have are quarks. We have fantastic names here: up, down, charm, strange, and top and bottom. And again, we see 3 generations, a pair in each of those 3 generations. And we see that the masses increase as we go from left to right as well. So we have these 12 sitting here, these 12 fundamental fermions here, but there's actually more, because there's an antiparticle for every single one of these particles. There's an anti-electron. For example, you know the positron as the antiparticle as the electron. There's also an anti-muon, an anti-tau, an anti-up, charm, anti-top, etc., etc. Now, they are exactly the same as their partner particle. They've got the same mass, they've got the same spin, they've got the same energy and momentum for all of the interactions that we see, but there's the opposite sign of the interaction. And in this case, it's the electric charge for many of them, and it's the isospin for the neutrinos here. So the electron here is negatively charged, its antiparticle is positively charged, that's the positron. The up quark here has a charge of plus 2/3, the anti-quark has a charge of minus 2/3. And I'll try and show you quick ways of trying to remember their charges and names and ordering as well. Now, when the quarks go into bound states, for example, the proton, we have 2 ups and a down quark that bind together to form a proton. There's also the antiproton, which is made up of 2 anti-up quarks and an anti-down quark. So we'll have all these anti-bound states, well, not anti-bound, but anti-states as well, made up of the antifermions. Right, now let's just have a look at the first generation here, because out of all of these 12 particles, our whole universe is made up of just 4 of them: the electron neutrino, and the up and down quark. Most matter in the universe is just made up of those. So why on earth do we need 3 generations? Nature is very, very interesting in that way. So what we have here are the lightest states, or the lowest energy bound states of all of those 12 fermions that we saw. So the electron is lighter than the muon and the tau. They can decay down to the electron. We'll see that later. And then the up and the downs, they form bound states. You can't have 3 quarks, and I'll show you that later. They always form bound states, and the lightest states of those are protons and neutrons. And if you're a nuclear physicist, this is all you need. You can actually stop here. Protons and neutrons are actually, and electrons a little bit, are all you're actually interested in. So as I said, for a proton, we've got 2 ups and a down quark. That's 2 quarks of charge plus 2/3 and a quark of minus 1/3, giving us an overall charge of plus 1. And then the neutron is 2 down quarks and 1 up quark, giving us an overall neutral charge. There's a few of these bound states that you'll need to learn the quark content of, and I would expect you, certainly by the end of the course, to be very familiar with what a proton and a neutron is actually made up of. It's just up and down quarks. You can try and work it out from the charges that you know you need to get for an overall neutral or plus 1 particle. If you struggle to remember a neutron, you've got DUD, that's a dud, it's a neutral charge, that might help you remember. And then for the proton, it's 2 of the other and 1 of the other. All right, so as I said, nature's not very simple. It's given us 3 generations of matter. Why? Why not 2? Why not 4? And these are very big questions that we still don't understand why there's 3. So for every generation, we have essentially a copy. It's essentially a replica as we go from the first to the second to the third generation. We've got a charged lepton, we've got a neutrino, and then we've got a couple of quarks, one of charge plus 2/3 and one of a charge of minus 1/3. So we're essentially copying and pasting, but with higher masses. They are distinct particles. A muon is not an excited state of an electron. A tau is not another excited state. They cannot, for example, decay down. A muon cannot decay down to an electron by emitting a photon. It cannot just release a packet of energy. It's not an excited state. It's a distinct state. So there's this symmetry between the three generations. We don't understand that. It's something that we're seeking to try and understand, and we don't understand why there's three and not two and not four. So lots of big questions to try and answer here. Right, so as I said, we've got two types of these fundamental fermions. Let's deal with the leptons first. We class them into leptons and quarks because leptons don't feel the strong interaction, whereas quarks do. Now, let's just have a look at the leptons here. So you've got your electron, muon, and tau, and your three neutrinos as well. They're all spin half. We've got 6 different distinct particles here. 3 of them are charged, the electron and the muon and the tau. And you can see their masses at about half a GeV here, about 100 MeV for the muon, and about 1.7 GeV for the tau. And then we've got 3 neutral ones, our neutrino, our electron neutrino, muon neutrino, and tau neutrino. Now, these are quite interesting. We will treat them as massless and stable in this course, and that's not quite true. We've got upper bounds on their masses, but we know that actually they must have some mass from neutrino oscillations. We'll have a look at that towards Easter. Now let's have a look at this. Electrons, muons, and taus are charged. So they can experience the electromagnetic force. That's the force that interacts with charged particles. So the electron, muon, and the tau experience the electromagnetic force, but the neutrinos are neutral, so they don't. They all experience the weak force, but none of them experience the strong force. Now, some of these are unstable. The neutrinos are all stable, but the tau and the muon are unstable, and they decay down via the weak force to the electron, and that's the stable charged lepton here. Now let's move on to the quarks. These are the ones that they all experience the strong force. That's what differentiates them from the leptons. Again, we've got these 3 generations, an up and a down, a charm and a strange, and a top and a bottom. So we've got a pair of quarks. One of them is plus 2/3, the other one is minus 1/3. So they're fractionally charged. If I try and write them like this in their pairings, up, down, charm, strange, top, bottom, all the ones on the top row have a charge of plus 2/3, and all of the ones on the bottom have a charge of minus 1/3. This is quite a good way to try and remember them. Even I have to sort of sit here and write that out sometimes just to confirm that I'm getting the charges right. Up and down are quite easy to remember. Top and bottom as well, because it's an up, down, top, bottom row. You can think of it like that. Charm and the strange I find a little bit hard to remember, but maybe you can remember this as some rearranged word of cut. And then there you go. You can try and get all the charges of your quarks memorized. Now, because quarks are charged, they will experience, even if they're fractionally charged, they will experience the electromagnetic force, and they will all experience the weak force as well, and all the strong force. So the quarks are actually quite busy with all of the fundamental forces here. Now, what's quite interesting is we never actually see free quarks. And we'll discuss this when we start to get to QCD. They are confined within bound states called hadrons. So like protons, like neutrons, and there's bound states of just 2 quarks as well, the lightest of which are our pions here. So we'll be talking about all of the zoo of our hadrons here, all the different combinations that we can have here later on in the course. Now, there's another sort of charge that comes with quarks, and I'll be able to prove that to you later. Like the electric charge comes in positive and negative, there's another type of charge associated with quarks, and it's called a color charge. There's 3 orthogonal charges, red, blue, and green. It's not an actual color, it's just the names of the charges. And it's basically a label for the strong interaction. If something carries a color charge, red, blue, or green, it will undergo, or it will be able to undergo strong interactions. So we'll be talking about that later. So for every one of these 6 quarks that you see, we have anti-quarks as well, and we also have 3 different varieties depending if they carry the red, green, or blue color charge. And see how things start to explode a little bit. Right, then hadrons. So quarks do exist in nature, but not freely. They're bound. They're confined within these bound states called hadrons. Now, we used to think that these were fundamental particles, and actually, macroscopically, they do behave like fundamental particles. But there are some small deviations from point-like particle behavior that we start to see, which when you dig a little bit deeper, you realize that they're made of other particles. They are composite particles. So there's 2 main types, depending on how many quarks we have in the bound state. We have mesons, which is a bound state of a quark and an antiquark. So we've just got 2 there, quark and an antiquark. And because you've got 2 fermions there, these mesons are then bosons. They carry integer spin. The 3 lightest mesons are the pion system. So where you've got up and down quarks bound together. So you can have an up and an anti-down, giving an overall charge of +1. You can have an anti-up and a down, giving you an overall charge of pi minus. So these are actually particle and antiparticle of one another. Or you can have a neutral pion, a pi zero here, which could be up, anti-up, or down, anti-down. And in fact, it's a superposition of both of those bound states. And I'll try and show you why a bit later. And that's neutral. So that's our lightest system. As I said, you will end up knowing the quark content of a lot of these hadrons. The pions and the protons and the neutrons are just some of them that you will end up knowing. But the pions are quite easy to remember with just ups and downs. You get the right configuration there for the charge, and it's not too hard to actually remember there. The next type of hadron you can get are when you've got 3 quarks in a bound state, like you have for protons and neutrons. So we've got no antiquarks here, just 3 quarks, or you could have 3 antiquarks, I guess. So these are bound states of 3 fermions. Overall, the baryon has a spin of half integer, so it itself is a fermion as well. So we've got the proton, which we've discussed, up, down, up, and the neutron, DUD. So again, if you struggle to remember this, the neutron is neutral, i.e. dud, and the proton is 2 of the other and 1 of the other flavor. So anti-baryons, we do have antiprotons and antineutrons, and there's a wonderful, actually an anti-hydrogen experiment using antiprotons at CERN. And that's a bound state of 2 anti-ups and an anti-down. Right, so let's zoom out a little bit and talk about nuclei. So we will be covering nuclear physics after Easter. And what we have there is basically a bound state of protons and neutrons. The number of protons we have is denoted by Z. The number of neutrons we have is denoted by N. And together we call them nucleons. And I will trip over my words quite a lot with this, nuclei, nucleons. So I'm very sorry about that. Hopefully you'll be able to follow if I do trip up. We denote the mass number of a nucleus. See, I've done it already. Nucleus with A, and that's simply the number of protons plus the number of neutrons. You've definitely heard of isotopes before, where you have the same number of protons, but you can increase or decrease the number of neutrons, and you could have lots of stable isotopes for a particular number of protons. You could also have isotones here, just in the perpendicular direction here, where you have the same number of neutrons, but varying the number of protons. And then isobars as well, where you have a constant number of protons and neutrons, and you can change the number of protons and neutrons respectively. And this will happen in weak decay, for example. We have a particular notation for our nuclei here, where it's the chemical notation for the nucleus here, like hydrogen, helium, lead, things like that. Then the superscript here, A, is the total number of protons and neutrons, and then the subscript to the left is the total number of protons. So you can work out the number of neutrons simply by their difference. So, for example, hydrogen with just one proton here and no neutrons has a total number of 1 here. That's quite easy. So we will write the hydrogen nucleus as 11H, or usually just P for proton. We could add a neutron to that and have something that we call deuteron, or heavy hydrogen here. So we've got 1 proton, 1 neutron, a total of 2 nucleons here, and then just 1 because it's 1 proton there. So we can write that as 21H, or just D for deuteron, not to be mixed up with D for the down quark. Usually we're dealing with the particle and nuclear physics quite separately, so hopefully we won't get confused there. And then moving up, of course, helium is our next one. Let's have 2 protons and 2 neutrons here with a total of 4 nucleons then. So we write helium-4 as 4, 2, He, or sometimes just alpha because they are alpha particles when we deal with radioactive decay. And onwards, for example, with lead with 82 protons and 126 neutrons, giving us 208 in total. Now, I think I mentioned it on the other side. In principle, you can have anti-nuclei as well. And there's this wonderful experiment called Alpha at CERN that's looking at the properties of anti-hydrogen. So that's an anti-proton with a positron attached to it. And that is a very, very fun and interesting experiment trying to see if there's any deviations between hydrogen versus anti-hydrogen. But that's as far as we've got, I think, with anti-atoms. They are very challenging experimentally, but it's really interesting to see if there are any deviations to what we expect between particles, antiparticles, or anti-nuclei and anti-atoms as well. So here's something that I know you recognize. This is the periodic table. We know that we classify atoms according to their particular chemical properties here. The ones that we're going to be dealing with mostly here are hydrogen, helium, and lithium, the lightest ones. Now, those were the ones that were made in the very first instances of the universe after the Big Bang. Everything else is made in stars, and we'll be having a look at the nucleosynthesis in stars in the course as well. And then we get up to a point, where are we? Let's try and get up to a point of the most stable nuclei, for example, lead. And to push beyond that, actually, you need the energy of a supernova to make those very heavy, rare elements. We also have something similar for the chart of the nuclides. So we're not bothered about how many electrons are around this, just for the nuclei themselves here. And there's more nuclides than there are elements, of course, because you can have different isotopes of a particular element here. So along the z-axis here, we've got the number of neutrons, so N, and then along the y-axis here, we've got the number of protons, Z. So for any particular number of protons here, for example, 28 here, you can have many different isotopes available with different numbers of neutrons. Now there's lots of different color coding here, right? So the black ones are stable, and that's roughly going along equal numbers of protons and neutrons. There are isotopes that are proton rich, are above this line, and there's those that are neutron rich, I have lots more neutrons than protons, and they usually decay down to the stable isotope, or the stable nucleus, versus alpha by doing beta decay, either beta plus or beta minus decay, and we'll have a look at this in the nuclear part of the course. Some of the heavier ones undergo alpha decay down to a stable state, and usually there's actually a very long chain of different alpha and beta and gamma decays all the way down to a stable nucleus. There are some that are highlighted here in empty boxes that display magic numbers of protons and neutrons. This may be the only time that you hear magic in your undergraduate course, but it's just special numbers of protons and neutrons that we actually see there's particularly high numbers of stable isotopes or isotones there. And we'll be having a look at why these magic number nuclei are particularly stable. Okay, so those are the particles, that's the matter. Let's move to the other side of the conversation and talk about forces. So forces in general are just something that pushes objects around and causes them to change. And you've seen this in electromagnetism. You've got these electromagnetic forces arising at a distance through your electric and magnetic fields. And it depends on the charges of the forces that they're acting upon and also the distance between them. This is not new to you. But it may be something that you didn't like. Even Newton didn't really like this and said that the idea that one body is acting on another in a vacuum without the mediation of anything else is a great absurdity. So he said that gravity must be caused by an agent, whether this agent be material or immaterial. He leaves to the consideration of his reader. So even Newton was concerned about bodies acting upon one another in a vacuum without actually exchanging any information. And he left this to the later generations to try and sort out. And so this is where we come into quantum mechanics here. So in quantum mechanics, the two charges here are actually exchanging a particle, your photon. Your electromagnetic field has been quantized, and that virtual field quanta, we call them gauge bosons, or in this case, for this force, photons. Now, if you have a look at one charge particle, exchanging one photon with another, a real photon, a massless photon, um, we will actually see, and I'll prove this to you, that it actually violates energy and momentum conservation. Now, we can do this. The Heisenberg uncertainty principle will allow you to violate energy, at least for a short time here, as long as delta E and delta T are roughly h bar. So that's if you've got two charges here exchanging a force, and they're separated by some particular range, it restricts the range that a large force can actually act over. So you can think of Coulomb's law like this as well. If you want a very large force exchange between two charged particles, they better be close together. But we'll discuss this a little bit more. We can actually get round this energy and momentum violation by looking at virtual particles, which will probably make your brain explode a little bit, but I promise you by the end of the course you will understand them. So if we actually consider not a massless photon, but something that could be non-massless, something different, or maybe even have an imaginary mass, we can then bring energy and momentum back into conservation. Something we really don't want to start violating. Okay, so here are our four fundamental forces. We've got you're very familiar. Let's start off with this one, for example, electromagnetism. You know this one very well, I hope. You've got two charged particles and they're exchanging a photon. That's as simple as the electromagnetic force goes. So that's something you're very, very familiar with. The strong force is very similar. Instead of just charged particles, it actually anything that's carrying the color charge, like quarks, it'll allow those to interact. And instead of exchanging a gluon, instead of exchanging a photon, a gluon is exchanged. So it's a different force acting between different charges. Not instead of the electric charge, it's the color charge, and instead of the photon being exchanged, it's a gluon being exchanged. And then we have the weak force, and this is the one that's actually responsible for radioactive decay, like beta decay and alpha decay. And this is the exchange of other bosons instead of the photon and the gluon. These are W and Z bosons, and all fundamental particles will interact via the weak force. And finally, and we will say very little about this, gravity. it'll act between massive particles, and the information is carried by the graviton. Um, we have yet to discover the graviton, and we have yet to successfully unite gravity with quantum mechanics at the scale that we're looking at here. So these bosons that are exchanged are really important. They actually mediate these four fundamental forces. They're all spin 1, so they're vector bosons. If they were spin 0, they'd be scalar bosons. So they're spin 1. And they interact, there's a symmetry in how they interact with all of the 3 fermion generations. So if you can understand how they interact with the first generation, you can copy paste that to the other second and third generations. And so the way that these gauge bosons interact with the matter particles, with those fermions, actually determines the nature of the fundamental force itself. And this defines our standard model of particle physics. So let's have a look at this. Let's have a look at the strong force. It's mediated by the gluon, and I'll show you there's actually 8 of them. It's spin 1, as they all are here, let's set its strength to 1 here, so that we're going to normalize everything to the strong force and compare the others. And the gluon is massless. Then the electromagnetic force. You're familiar with this, the massless photon. It's about 1% of the strength of the strong force. So the strong force really, really is very, very strong. It's very aptly named. But the electromagnetic force is about 1% of the force of the strongs. Then let's go to the weak force. Instead of just one type of boson here, we've got 2 charged ones, the W plus, the W minus, and the neutral Z boson. They're all spin 1. These bosons are actually not massless. They are massive. The W bosons are about 80 GeV, and the Z boson is about 90 GeV. And the strength of the weak force is even weaker again, about 10 to the minus 7 of the strong force's strength. And let's include gravity just for fun. We think it's the graviton, which should actually be spin 2. In the strength of gravity, well, we all know that. We can all overcome gravity really easily just by picking something up. We know that the gravitational force is very weak. And it's about 10 to the minus 39 of the strong force. So very, very weak. And it's not included in the standard model. The others are. So there's something missing in the standard model. We know it is. And it's one of these things that we would love to incorporate in. But as yet, it's missing. So we'll be talking about the strong electromagnetic and the weak forces in the course. Now, the range of the forces is dependent on the mass of the particle that's being exchanged. Those gauge bosons, the photon, the gluon, the W, and the Z. So you can have a look at Heisenberg's uncertainty principle for this. We know that energy is E equals mc squared. We plug this into Heisenberg's uncertainty principle, and you'll get a sort of time limitation on the force, which you can translate into a range for the force. So the range should be inversely proportional to the mass of the particle that's being exchanged. So for the strong electromagnetic and gravitational forces, those are massless bosons that are being exchanged, so that their range is infinite. So let's have a look at the strong force up here. Its strength is infinite, and we have a 1 over r. We have a 1 over r distribution here. It's going to drop off here, but I'll talk about that in a second. The electromagnetic force is a bit weaker, but again, it has an infinite range with its strength dropping away as you get to higher ranges. Gravitational force, extremely weak. I mean, this is a log scale graph, so it's very, 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 very weak. We won't be discussing it any further. Now, the weak force is mediated by massive bosons, those 80 and 90 GeV, Z and W bosons. And so its strength actually drops away with the distance. And we have a typical range of the weak force of around 10 to the minus 18 meters. So the weak force is generally, you'll see it at very small, well, it's very important for the nuclear decay over those very small ranges that you get to down there. Now, the strong force, as I said, is doing something a bit weird here. For when you're discussing quarks, free quarks, which don't really exist, you're exchanging massless gluons, and that's fine, and it will go on infinitely. But actually, what happens as you get to larger distances, we have, instead of a gluon being exchanged, we actually have massive pions being exchanged with a strong nuclear force. Those are massive, about 140 MeV each, and that actually drops away. That means that the strength of the strong force drops away when we're talking about interactions between hadrons. So nucleons will experience quarks will experience the fundamental strong force, but at larger distances, they're actually confined within hadrons, sort of at about 2 femtometers. They're confined within hadrons, and we need to then discuss how the hadrons interact with one another, and not just the quarks. This is why nuclear physics gets very complicated. And instead of exchanging a gluon, they exchange a massive particle. So the strength of that force drops away with distance there as well. Okay, so there's a very basic summary. We will be going into far more interesting detail in the rest of the course. We discussed the differences between particle and nuclear physics. We had a quick look at matter, the different generations. We have quarks and leptons, and then the bound states of hadrons and nuclei as well. And then the forces that interact between them. We had a quick comparison of classical versus quantum mechanics. So we had a look at our 4 fundamental forces and the gauge bosons that are exchanged for each, and how this can or cannot limit the range of those forces. So what we're going to do next in the next chapter is, it's a 2-hour chapter. I'll record it in 2 parts. We're going to have a look at the kinematics of interactions. We're going to have a look at decays and reactions. And this is a common chapter for both particle and nuclear physics. It may be a bit dry, it may be a little more boring than the other chapters, but you need it to lay the foundations for what we're going to go on to. Once we've got all of that under our belts, we can go and have a look at the more interesting parts of particle and nuclear physics. Okay, so that's it for chapter 1. Make sure you get the books. Keep an eye on the webpage. Everything will be posted there. And please do get in touch if you have any questions or would like to discuss any possible misunderstandings or understandings of part of the course. See you on the next chapter.